you will see that actually we have interpretable deep learning, which is like, explainable. We have radiologist-centered, like the human in the loop AI, and like hybrid intelligence, as you can see from in another title. So our laboratory, we are trying to develop something more trustworthy that, the radiologists, clinicians, physicians, patients, and even ourselves, like software engineers, scientists, can trust. So that is the mission of our laboratory, and also, the similar to like this talk today. So we have, our laboratory, we have developed a lot of deep learning algorithms and get, international recognition in different challenges, like mostly it's like segmentation and, the diagnostic challenges. And we got, awards from, especially two of our well-known studies. One of them is lung cancer screening, and the other one is the pancreatic cancer, the screening. This is one of the highlighted topics in Fox TV about our lung cancer screening study. I'm just going to skip very quickly here.
And the number of lung tumors that are not caught. Try to identify what is normal cases in a crowd. But they feed nearly 1,000 scans of different lung tumors into their...
At that time, 1,000 was a good number. Nowadays, it is not. But it was very successful algorithm, still being considered one of the, state of the art for detecting lung tumors and characterizing them. And another one is similar to, the pancreatic cancer.
Biggest challenges and with the Mayo Clinic in Florida to develop a similar system.
So we have developed this algorithm with Mayo Clinic. So the idea is that actually, for lung cancer, there is a screening paradigm. So patients go to CT scans and doctors actually screen them, and radiologists look for these tiny tumors if they have in their lungs, and try to actually detect this at early stages. And if you keep them in this early stages, you save their lives. For pancreatic cancer, it is even more difficult because there is no screening paradigms. Most of the time, cancer is detected like by chance. So in this actually project, our idea is to find the cystic lesions in the pancreas and use deep learning algorithm to try to understand which lesion is going to turn into cancer in the future. And we are trying to do this with the the robust and the trustworthy AI algorithms. And if this is successful, so far actually we got pretty good results. If this is successful, this is going to change and probably add a screening paradigm for pancreatic cancer research.
Biggest challenges in cancer
pancreatic cancer actually management. So like I said, briefly, we are trying to, in our laboratory, we are trying to develop AI solution which are trustable. Like it should work in different environments from different, the images and the clinical parameters when they come from different sources. Your algorithm, your system should give consistent results. And if possible, try to avoid biases and many other fragile. So we are trying to include the expert in the loop for this decision mechanism system, so that the two brains, even one of them is AI, the artificial is going to be better than one brain, and then they will also complement to each other by combining their strengths and try to avoid their weaknesses. So even our laboratory's name is hybrid intelligence. Try to to combine this the global and local informations. Like we are still much better than AI in high level recognition task, and they are pretty good at the local tasks. So we are trying to actually combine a true collaboration between the AI algorithms and the human. So putting the human, in our case, this is the expert physicians or radiologists or pathologists in the center of this decision mechanism system, and try to learn from both sides. So this is, of course, like this one aspect. There may be actually many other roadmaps in addition to these three major steps we define towards a trustworthy AI. So in order to get an AI algorithm to be trustworthy in high-risk applications, like in autonomous driving, like in medical diagnosis, and all other high-risk applications. So we define at least 3 major steps. One of them is developing a robust algorithm. You should develop an algorithm which is not easily broken, fragile, and then your model should be interpretable. It should be, beyond these black boxes. And if possible, especially like medical diagnostics, so we are trying to put the expert in the loop for several benefits, like avoiding biases and trying to complement the weaknesses of the AI systems. In this talk today, I want to actually talk very little about algorithmic robustness, as previous speakers like from yesterday and today, and many of you actually, is when you have projects, you are trying to improve the current algorithms, develop new algorithms based on the available knowledge. And I think most of the research is ongoing on this, developing the new systems. And I'm sure many of you, aware of this. So I will talk little about algorithmic robustness. And more in the time, I want to talk in the interpretable methods, particularly for, the deep learning. And then I want to show actually one of the latest method that we are working, and how this is actually better than the other methods. And then at the end, I want to show one showcase, which is how we can put the expert in the loop to have the more trustworthy, to have a hybrid intelligence systems, which I will show. We are using virtual reality systems and mixed reality systems like with HoloLens. But I will focus on this talk in the eye tracking system that we are connecting human with the AI in the radiology rooms. So very briefly, for algorithmic robustness, I mean, almost every day, the new algorithms are coming. So I'm sure your mailbox is also full of Archive, and Google Scholar is very new algorithms are coming, mostly incremental, but so many different versions of this. Nowadays, the most popular ones are like transformers and diffusion-based systems. And as you can see in this graph, that actually their operations like GFLOPS is increasing, and we see that actually many algorithms are replacing the state of the art every day. So this is very fast pacing, the time actually we are witnessing. So when we have all these algorithms, one of the things is that actually we should be really careful about their generalization ability, and if they can work in different environments in most the robust settings. I want to show one example just before transformers were taking the lead on this. Actually, in our group, we were working a lot in the capsule algorithms, and we still believe that the capsule algorithms are pretty robust compared to the other deep learning algorithms. It didn't fly well, universally. It has not been shown superior to like the CNN-based algorithms, but in some of the cases, particular application we have shown, and some other people shown, including Hinton himself, that capsule algorithms have some state-of-the-art superiority in certain tasks. So why capsule neural networks compared to convolutional neural networks? So if you see on the left-hand side, you see actually two faces where if you put them into the actual convolutional neural networks, it is gonna classify both of them as face, because they have these objects parts are the same, but the spatial relationships are broken. For the capsules, actually, these object and parts relationships are actually kept. It is preserved. This is very important, especially if you are looking for developing something, looking for like biomarker discovery, looking in the tissues and the tumor and environmental, the relationship, and many other things. So, so that is actually how capsule is helping. Instead of like a one-point prediction, capsules have vectors, and the vectors are actually keeping this special information about objects and parts. It has several benefits, like it requires less training data for good generalization. And as I said, like it preserves the part-whole relationship and the shape information. And you know that actually in CNN, texture is dominant to the shape, and you have to deal with, and if you are, for example, looking for more shape information, you have to design your algorithm accordingly. Based on these two concepts, the capsule networks and the vectors preserving the part-whole relationship, we have developed several algorithms. One of them is the first one. It was in 2018, just 1 year after the CapsNet. It was the first ever segmentation-based capsule neural networks. And then, we use this for diagnostic capsules, like for classification for larger scale images, explainable capsules for putting the structural explanations into the capsule, the Bayesian capsule for uncertainty quantification, and for object detection, and many more. Pretty robust algorithms. It requires less data to work. Of course, it has also drawbacks, like it is computationally more heavy. It's not really straightforward like other convolutional neural networks to run these. Students, to my experience, they hate working with this environment. It's very difficult to work with all these vectors. However, once it works, it's pretty stable and very robust algorithm. Again, I will just keep this algorithmic robustness pretty short, as you are already aware of this, and many of you already work on this topic. From the algorithmic robustness, I can say not only accuracy, but there are the other metrics we should pay attention from the algorithmic robustness. For example, using the less designing an algorithm that accepts less parameters to train, like avoiding the overfitting. And using the less and or even noisy labels to to converge, domain generalization, like making sure that you have a good generalization, and there are many other things also, like the audit, verification, efficiency, and even carbon fingerprint is important when you consider the evaluation of your algorithm. Not only accuracy, but we should also look at all those things and look at the behavior of the algorithm in different settings. That's gonna make your algorithms robust. Once your algorithm is robust, I think this is one of the first major steps towards a trustworthy AI. It's not enough, but it is important to have this very first step. I want to spend more time on the interpretable methods, which is also a hot topic for the recent, the 4 or 5 years now. It is expected that your system should explain their decision. Like, deep learning is telling you one output, but if it doesn't explain why it chooses that output, then especially for high-risk application like in medical diagnosis, this is not really desirable. The question is like, what is this really interpretation? So it's called also explanation, interpretation. So this is really subjective topic. This is a very nice paper actually to explain like interpretable, but interpretable to whom? So the interpretability is a like domain-specific notion. So there is no one-purpose definition for autonomous driving, for medical diagnosis, and for other, the task. This interpretation changes. So it should be defined prior to task actually that you are working. I would like to actually focus on two subtopics under the interpretable deep learning. One of them is like visual explanations. It's famous, like almost everybody knows GradCam and other saliency-based metrics actually, where basically these methods actually showing the most important regions in the signal, in the video or in the images that is associated with the outcome. The second one I will focus is like the structural explanations, which is the more high-level explanations. And in some people actually use like the concept vectors. There are also the causalities and all other things, but these two are especially important for high-risk application that I'm gonna focus. Let me start with the structural explanations. So, we work on this, the diagnostic and, the prognostic applications. So here you see a radiation therapy example where a patient goes into this therapeutic the system. So, before the treatment, they go to the CT scan, and after the treatment, they go to another CT scan for the radiation treatment. So the doctors are trying to understand, for example, one of the the topic here is to give the high dose to the tumor regions and the minimum dose to the nearby regions. And they try to understand if this tumor is going to respond to the the treatment or not. If you know this beforehand, and then the treatment strategies can be adopted. It's very important topics, and AI can help. And there is a segmentation, classification, and the dose distribution prediction. So many actually tasks can be done with AI. When the tumor changes its shape, and let's say it responds to the therapy or it doesn't respond to the therapy, then the radiation oncologists, physicians, they want to know actually what is the reason why this algorithm is telling that this patient is going to respond to the treatment. There may be some morphological changes, maybe scar tissues is happening, location of the pathology, and the density you measure, or texture or shape of the the tumors. All those things can change and can tell us something about this treatment. And usually radiation oncologists and radiologists actually are looking at these radiographical changes and what happens. And there are also even standards actually they follow about these changes. And if your algorithm is telling the reason in their language, in radiation oncologist language, in radiologist language, actually, they start trusting this algorithm more. So not only it should say this patient is going to respond to the therapy or not, they should also tell something about how visual attributes are going to change in the tumor and what does this mean. That is actually called structural explanations. And this is just one example from radiation oncology. Another one here, you see MRI images for the pancreas. There is a cyst. And if this cyst is going to turn into cancer or not, let's say your algorithm is saying that, yes, it is going to turn into cancer. And then the next question is, okay, why? In which clues, in which changes actually your algorithm is thinking that this is going to turn into the cancer. Then again, like morphological properties, location, shape, size, texture, and all other structural information can be used to support this decision. You can consider this. Okay, this is another example before going into the details. Like this is the lung nodules. There are like 6 visual attributes that radiologists are actually mentioning this in their report. The margin of the tumors, lobulation, speculation, and many other things. So not only that, like this lung tumor is a cancer or not, like a malignant or benign, but they also mention about these radiographical interpretations. And the expectation is that actually your deep learning algorithm should say this tumor is, for example, malignant because of, its sparsity is high, margin is that, lobulation is this. Is kind of, the vocabulary they should use to convince the physicians. And there should be also like a meaningful relationship between this kind of the outcome and the associated task. So all this structural interpretation actually can be modeled in different ways. One way to consider this is like, let's say, you have an algorithm, like, here it is like capsule algorithm, but it can be transformers nowadays, famous algorithms, or, some other things like even GAN or, the simple CNN or ResNet. So for a given nodules, you have a network and it predicted diagnosis like malignant or benign, like you see in the bottom part. There is a segmentation part for reconstruction, just regularizing the system. you don't need to focus on here, but let's say you have this predicted diagnosis, malignant or benign. So for the visual attributes, this structural interpretation, we need how radiologists are interpreting these nodules, these tasks, like at least 6 of them actually in the previous slide I mentioned. So this can be considered as the separate task, but they are all related to each other. So the problem turned into a multitask learning problem here, because these tasks are not completely independent and they are associated with the predicted diagnosis, or the malignant or benign. A multitask learning here is a good potential solution. Not only just the lung nodule diagnosis, but it also gives the visual attribute that is associated with the diagnosis. These kind of systems are more trustable, and actually we are using this in our hospital, in our research packs, and radiologists actually feel more comfortable when they see this radiographical interpretation in our report, when we give some percentage of the predicted diagnosis. A more trustworthy relationship actually is being built by this way. And this is called like the structural relationship, structural explanation, sorry. Some of the take-home messages for this radiographical interpretation or structural interpretation is that actually this is really necessary for practical explainability. It gives you, the high-level information about the topic that you are interested in. Maybe one of the difficulty here is that for different problems, you need to define this again and again, and at the beginning of the problem. So for pancreas is different, for lung it is different, and for autonomous driving, these are all different. So interpretability is a subjective, the definition, and it needs to be defined at the beginning of the problem. And the consensus, even for like lung or pancreas, consensus may not be easy. Different radiologists may interpret things differently. So there should be a consensus about how radiologists actually are interpreting. Some of the common senses and the common tasks should be used for the structural interpretation. The second, I want to actually show also this visual explanations part. So far, it was like more high-level applications, or this explanations were there. And it is this, the similar in pathology, similar in, this autonomous driving as well. And now it is the visual explanation. This is really common. These visual explanations are based mostly is the salience-based method, providing insight about the decision-making process by assigning like relevance scores to each input variable, the videos or the images or any other signal. This common examples from computer vision. So there is this input image, and if the target is like the dog, for classification, there are many different actual salience-based methods, but the second one is the GradCam mostly used one of the mostly used one. It is showing the most relevant regions in the images that is associated with the outcome. That is the one of the visual explanation cases we have used, and some other people actually I think is using this a lot for showing the classification results and which informations from the images are mostly used. This was our COVID studies, but to be honest, actually this is a very fragile method, and most of the time, including us, actually is using really, the cherry picking to choose the best slices, to showing that, the algorithm is learning from the relevant regions. Many drawbacks for these methods, these visual explanation methods with the saliency, they are mostly actually post hoc. It's not inherently explainable, and there is no really reasoning about these interpretations, and it is easily fragile if there is, the different the artifacts, noise, and from different centers, images and videos or signals. Actually, this can be easily fragile. Instead, actually, we developed something very simple in our laboratories based on a very famous topic, is information bottleneck from information theory, signal processing. That is much robust than actually GradCam, and we have used this actually almost everywhere, show the benefit of this. So the idea is very simple. So we are actually compressing the input a lot. In any deep learning architecture, you compress the information, and then you try to pass the minimum information from encoder to decoder, and make sure that that information is suitable enough, like strong enough that your output is correct. So for any given signal here, this encoder and decoder part in the bottleneck region between X and X tilde, you compress the signal and you make sure that actually your output is still the correct Y. So how we can do that? So it's like you are minimizing. So one way is to actually add a lot of noise there and look at the mutual information or entropy, let's say. So minimize the information between X to X tilde, which means actually you are compressing the signal, and then maximizing the information from X tilde to Y. Like your classifier still tells you the truth. So this way, actually, you can identify the minimum necessary information from the input that tells you the output, the classification. I'm going to show here the MRI pancreas region. Again, like this algorithm will work for any architecture. So you have here is just the res-nest algorithm, and you have the X in the bottleneck region. Actually, you have this X, and then you compress the signal. You compress the signal by adding just noise, random noise, and in the form of actually the mask, and then your outcome should be the the same, so that actually we can use those the regions, the minimum necessary regions that gives you the results. Okay, this is like an optimization algorithm. So initial bottleneck you define, and you randomly perturb your mask, and you try to update this mask during the optimization, so that actually your binary outcome is maximized compared to this with respect to this X tilde. I'm going to show some results. Like the first row here, this input image is actually MRI, is the pancreas, very difficult organs. Even segmentation is very challenging actually here. When you ask radiologists to outline this, actually it's coming a lot of problems. It's not visible, it's very challenging organ orientation and the location of it. So the first row here show the IBA is the information bottleneck based visualization algorithm. As you can see, most of these attention regions, these saliency regions are inside pancreas and showing where the cysts are, of if the cyst stratification is correct or not. While GradCam is this most famous algorithm, is actually showing almost all over the place, is failing actually here. So this is MRI example. It is another MRI example for IBA is showing some nice localization of the the cystic regions, while GradCam is actually failing. One more example here, again, like very challenging case that GradCam is failing. So this is relatively easier problem compared to the MRI. This is the COVID-19 CT cases. And this on the left-hand side, this CT image is actually from a healthy subject. So there is no COVID, no pathology, nothing. And information bottleneck-based visual interpretation method is showing nothing. It is true, while GradCam is picking up some random places. And another actually input here, there is a tiny, the pathology in the left side of the lung, just there. It is ground plus opacity. And IBA is localizing this very nicely. And this is also showing that actually this can be used for like weakly supervised, the localization, like without labeling, actually it can also locate the pathology nicely. And GradCam is showing nothing here. Another cases here, some again GGO pattern. very tiny, very subtle, and IBA starts showing again, those regions, while GradCam is showing all over the places. So even if your algorithm is telling that your result is true, and if you look at the GradCam, and then you cannot really trust this algorithm, right? So it shows almost everywhere. So you need a really good algorithm, robust algorithm, and a visual actually it shows where the information is taken from for this classification cases. We have compared this with the the GradCam algorithm, this IBA algorithm, in 4 different radiologists and physicians mixed, and in all cases actually IBA was shown to be much better than GradCam, all these experiments. I'm gonna skip this, and we have shown actually how satisfactory IBA was on localizing this stuff, because it is using the minimal information. So there is a drawback that for a large tumor or a large scale, the pathological side, IBA may be underestimating those regions. This is the current drawbacks of the IBA, but still working much better than GradCam for localization. And in all cases, again, IBA was shown to be much better than the this GradCam algorithm. The take-home message for the visual explanation part is that actually this model verification requires visual interpretation check, but your algorithm should be robust and showing with the minimal information, it should show where the most important region in the signal that is associated with this outcome. And I think it is very important in terms of biomarker discovery research and for imaging marker discovery research. So we are paying special attention to this part, not only like the clinical or practical applications like structural explanations, but visual explanation can give a lot of insights about the where the algorithms are paying attention in the images for outcome prediction. So the most of these algorithms are really cherry picking. So we should be really careful about all these algorithms and try to develop something more robust and trustworthy. So IBA is one step towards this, getting the its root from information theory and signal processing. And currently it is like the promising, but it needs to be also developed further, like for different scale pathologies, how this is gonna actually localize in high accuracy. Okay, so that was the interpretation part, and in the last part actually I want to talk in the how we can increase the trustworthy AI further by including the experts in the loop system. So algorithmic robustness is the first one, the first major step, and your system should be interpretable to increase the trustworthiness. And in many cases, especially in the radiological applications, or the diagnostic and the surgical AI techniques, we believe that putting the expert in the loop and making the connection between the algorithms and the computers can increase the trust, and by increasing the efficiency, accuracy, and avoiding the potential biases and the weaknesses. Different techniques can be used for this, like this DeepMind was, people were using this joystick when they play game, and the joysticks and these games were the interface between computer and human. In our case, like virtual reality, mixed reality, and other, even keyboard, mouse, these are all interfaces. But I'm gonna show an eye tracking system which is very suitable for radiology rooms, and then we can combine a radiologist actually screening with the deep learning paradigms. The problem is that actually radiologists are great. Their eyes are very specialized, I want to say, like when we were doing a simple experiment in University of Pennsylvania radiology, there was a little dust in the screen, and radiologists were very, very careful that they were all thinking this dust, if it is a small tumor or something. So they capture things very nicely, but at the same time, there are so many biases in radiology. So yeah, they are great, but they also miss the tumors for different reasons. So there is this nice article in actually Radiographics journal. It explained the biases in radiology and how and why they miss, and there are misinterpretations. I want to actually focus on these two of them. It's very critical for us in radiology screening of the cases like in lung cancer or other, the screening paradigm. One of them is called satisfaction of search. So when the radiologists find one tumor, for example, they may actually decrease their vigilance to or awareness to find the other, the pathologies potentially ongoing. So it's like a losing interest in the other parts because they think they already captured the main one. And another one is like inattentional bias. This is something like, they are missing this tumor or, the pathologies because they are maybe hiding in the plain sight due to unexpected location or nature, or they may be very similar to the normal tissues as well. And again, like there are many other biases, like the confirmation bias, availability, fatigue is another one. But we will focus on these two of them. And because in our laboratory, not only we are trying to actually develop algorithms to detect those tumors and quantify, but we try to understand also if radiologist screening, like their screening performance, is including some bias or not. This is very important because at the end, radiologists are defining all this diagnostic, the outcome, and we want them to be bias-free. So one way actually is, so I want to actually show this nice example that, so radiologists are actually, this 35% is really changed actually recently. This is the old statistics, but quite a large percent of lung nodules are typically missed during the screening procedure, especially when the tumors are very small. They don't see it. So if you don't see it, then, you miss it. And another problem is like overdiagnosis, that is like for a tumor which is not malignant, radiologists and the physicians can say this is like malignant, and this can lead into the unnecessary treatment. So all this bias should be actually removed. So when you look at this screen, actually this CT scan, on the right-hand side, you see a tumor in the bottom part of the lung. And this is a famous study where if you just focus on the CT scans, you will see there is actually a gorilla on the left-hand side. And 20 out of 24 radiologists, they didn't really notice this, the gorilla. So this is very famous vision experiment. It's a satisfaction of search because they see the tumor on the right-hand side, and then, they reduce their awareness for looking for other things. So this is showing actually how fragile screening can be. And, this is one of the weaknesses that deep learning can help radiologists to overcome. At the same time, deep learning is also producing a lot of false positives, which humans are much better than them. And then humans, like the expert, can help them to reduce those biases. So there is a need to have a true collaboration between them. So we are using this desktop-based eye tracking system to get feedback from radiologists. And our system is the real time. It's not just the laboratory studies, but we put this system into the radiology rooms. It can work in dark and light. It can work in multiple screens. And radiologists are allowed to do this, scrolling, zoom, and other, the contrast, brightness, and measurement kind of gestures. And they can also, like to scroll into the different directions. So the three-dimensional view is possible. It took really a lot, like 4 or 5 years to set up all these details. Unlike other actually vision experiments with eye tracking, which is very controlled under laboratory environment, they are very useful as well, but not really practical. So we have built up this. Initially, we were using actually eye tracking glasses, but we switched into desktop glasses where radiologists do not need to actually wear anything. So this is one of the very initial systems in 2015, 14 or 15. So the idea is that actually eye tracking glasses actually here, radiologists look at the screen, we collect their eye gaze patterns, and these eye gaze patterns go to the CCAT, which is collaborative CAT. You can consider this like a deep learning. And then we change the attention regions in the deep learning to focus on the most important regions coming from biological attention regions, not the computer attention. So the gaze data is coming from eye tracking. And what we have done is actually we represent the gaze as a graph. From the graph theory, we represent them as a graph, like the vertices and the edges. And then, since it is a lot space, we just actually sparsify, the cluster them, and we just use some of these, the nodes, not all of them, because there are so many actually in the nodes in the screen for the gaze map. And then we do also graph sparsification. I'm going to tell why we are actually doing this sparsification system. And the remaining, the minimized gaze patterns are feed into the images with the deep learning to find the tumor, segment it, and then classify it, whatever the task is. When we start this, we were using like the CNN algorithms. Then we actually replaced all of them with the capsule net, and recently actually we replaced everything with the transformers. So it's a strength that actually, so this system is not really changing, but the algorithms are actually, we are putting the more advanced algorithms as the time goes on. So there is a gaze analysis, visual attention part, and the machine learning part for the true collaboration between radiologists and the AI. This is our very recent study that we replace everything with the transformers. The original work is the same. All these systems are the same, but just we replace with these transformers. And then just previously, actually, we also try even graph neural networks instead of just the graph. I want to show these 3 radiologist visual the visual screening trajectories. The first row is actually showing the first radiologist eye gaze map in the edge, in the node versions. And the third row is showing actually how we cluster and sparsify. So those points are the most important points to really look at it. This is the radiologist second. It is the same for the same actually images, CT scans for lung screening they do, trying to look for lung tumors. And this is the third radiologist. As you can see, their attention maps, their gaze maps are all different. The first radiologist is the actually most experienced one. Screening is finished like in 121 seconds. It's 2 minutes actually. He finished the screening. And the third radiologist was the most, it was actually fresh graduated radiologist. We taking like 5 minutes and looking at all over the places. So although, these radiologists are looking, differently, we were able to sparsify their findings and put all these the sparse nodes into the, the deep learning. So this is also telling us that it is possible to personalize the deep learning algorithm based on this connection between, these algorithms and the experts through eye tracking system. And this is like another study where our radiologists were trying to segment this brain tumor for volumetric and then quantify them. And as you can see, he's so relaxed that there's even a coffee there, and he can, look at other screens and even other parts, and then it's pretty relaxed environment, unlike the other strictly controlled laboratory environment where we collect all these gaze patterns for different tasks. Here it was the segmentation, like labeling. You just look at it, and then we have on the background some UNet-based algorithms are working for roughly segmenting and then refining for data collection purpose. This is our new device. This is actually not the big screen, but just the control screen. We are using actually different eye tracking systems to to check their feasibility and the accuracy. That is the very recent one, and we have used this for the different segmentation from different sources: CT, MRI, ultrasound, and the PET. And this is important because one of the most difficult thing in medical imaging is that to collect all this labeled data. It's very expensive, and so we are thinking that we can roughly segment the organs or pathology even during the routine screening of this routine days of the radiologist. And I want to show just one example where radiologist really didn't look at the red part of the the CT scan. The green part is on the left is showing where they look at it, radiologists, and the red ones is like they didn't look at it actually. So there is no AI gaze maps there. We go there automatically, and then for those regions that radiologists didn't look at it, actually we run the algorithm, deep learning algorithm, to see if there is something missing there. So this system is telling radiologists actually, hey, you have a tissue at risk for misdiagnosis. And then actually this is increasing the trust because it is helping radiologists, and the radiologists' help is, like I said, actually we learn from how they look, how they search. And on the right hand side now you see real-time segmentation. Actually we use very simple visual prompt for SEM. This segment anything model recently become famous by Meta, Facebook, and we didn't even actually do anything, just a little fine-tuning. And this red dot actually is just where the radiologists are looking. It's real time. They just look at it and actually we segment. And it's pretty, the easy setup. And then I think there is a huge opportunity here to actually fine-tune the segmentation and use these kind of systems in real time. And the segmentation is possible. Classification can be possible too. This is the old system on the left-hand side. So the idea was, can we use this for multiple screen? Yes, this is multiparametric MRI of the prostate. And we can even understand actually how these radiologists look at, the different MR component like the T2, T1, diffusion weighted images, and in which order he is looking at to find the diagnosis of the prostate cancer. So this kind of, this eye movement actually is telling us, how the fusion operation is actually happening in the visual world. And most recently, we combine all these things with the speech recognition, with eye tracking. It's like a full system that we are connecting with the AI algorithm to do tasks like, the segmentation, classification, and all other things. And especially after ChatGPT, actually, we are using this technology as well to do our task in a fully automated manner. I want to show also one example, which from non-medical imaging cases, where, as you can see here, there is this inspector. Instead of eye tracking, here we are using the mixed reality headset. And probably one of the first time actually we see civil engineering or computer vision is borrowing ideas from medical imaging in the medical image analysis, let me say. And here, the crack and the breach and all those things are considered as a pathology. So we do pathology detection and segmentation, right? So here the inspector is doing from a distance, looking for the breach, and then do the detection first and then quantification. And there is actually interaction here. So from his, the gestures, the algorithm learns, and from algorithm actually show him where to look at it. So this is like a real collaborations as well. Little movie here. So this is the headset view. inspector is looking, and at the same time we see the crack immediately, and then he can actually start the analysis just by scan damages or analyze damages, and it shows actually where it is, and then it automatically actually report it to do the cloud systems for general inspection. And the SPAL and all other different the cracks actually can be automatically done actually by this way, and it is all real time actually. Okay, that was it. Thank you very much.
Çok teşekkürler hocam.
Ben teşekkür ederim.
Acaba sorular var mıdır?
Öncelikle sunumumuz için teşekkür ederim. Benim sormak istediğim şu, hani ben de bir tıp doktoru olarak mesela bir BT ya da bir MR'a bakarken özellikle hani Amerika'da, Hollanda'dan, farklı yerlerden de hani sizin ekibinizde de hekimler olduğu için söylüyorum hani. Her birimiz çok farklı biçimde bir radyolojik görüntü okumayı öğreniyoruz. Çok farklı ekoller var. Her fakültenin, her hocanın kendi okulu var diyebilirim hani.
Evet.
Sizce bu tip bir çoklu ekolde bizim hani, çünkü mesela sizin az önce gösterdiğiniz bu hani BT okuma biçimini söyleyeyim, abdominal BT'yi mesela, hani o sırayı çok net tanıyorum. Yapan kişinin de ekolünü büyük ihtimal söyleyebilirim. Ama mesela ben öyle başlamıyorum. Mesela ben karaciğerden yola çıkarak giderim. Karaciğeri merkeze alırım kendim okurken. Siz hiç şeyde denediniz mi? Beyin BT, SVO hastaları, inme. Çünkü
Evet.
özellikle inme hastalarında mesela bir nöroloğun yaşadığı en büyük sıkıntı şudur. Bir yandan servisiniz elinizde patlıyordur. Bir yandan acile yeni inme hastası yatmıştır. Zamanla yarışıyorsunuzdur. Penumbra alanını korumaya çalışıyorsunuzdur. Penumbra inme geçiren alanın sağ kalan, ölmeye 3 kala olan alanıdır. Öyle anlatabilirim. Burada hani doktor değil çünkü burada kimse. Hani o tip bir çalışma hiç yaptınız mı ve bu konuda özellikle nöroloğu ya da radyoloğu uyaracak, böyle diyecek hani burada penumbra alanı var, sağ kalıyor. Hani ilgilenemeyecek gibiysen hani başka birine hani haber ver gibi bir uyarı sistemi kurmayı denediniz mi? Çünkü şu an nörologlar, radyologlar özellikle hani Türkiye'de bu çalışma başlarsa bütün üniversiteler bu işin kapısına girecek durumda hani. Çünkü biz de artık bu yükü kaldıracak durumu geçtik hani. Bu iş hani insanın kaldıracağı çığırdan çıkmış durumda.
Doğru, doğru. Evet, hem CT stroke çalışmamız var, hem MRI brain tumor çalışmamız var. Ultrason da var. Bu bebekler için de kullanmaya başladık bu şey için. Yeni doğan bebeklerde ultrason yapıyorlar işte şey kafasına. Onun için de var. Şimdi değişik şekilde okuyorlar radyologlar. Dediğiniz doğru. Scanning olabiliyor, dragging böyle zikzak şeklinde olabiliyor, drilling oluyor, gidip geliyor böyle. Hepsindeki şey, temel şey şu ama ya belli bir şey cover ediyorlar, belli bir bölgeyi. O cover ettiğimiz region'a bakıyoruz. Bir de cover olmayan bölgeye bakıyoruz. O cover olmayan bölgeler deep learning'e tekrar gidiyor. Yani bakmadıkları yerleri bir daha test ediyoruz. Orada bir şey varsa onları highlight edip radyoloğa geri gösteriyoruz screening bitince. Yani orada bir şey var, alert sistemi var. Bir de işte bu cover edilen yerlerde visual attention, yani bizim algoritmanın bulduğuyla doktorun bulduğu yerler overlap oluyor mu olmuyor mu ona bakıyoruz. Eğer biz false pozitif region'lar varsa bunu mesela gösteriyoruz doktora feedback olsun diye. Eğer false pozitifse doktor tıklıyor o bölgelere. Biz onu active learning ile geri işte algoritmaya koyuyoruz ki evet bu bölgeler yani false pozitif. Dolayısıyla model update olmuş oluyor. Yani iki türlü çalıştırıyoruz. Bir bakılan yerler, bir de bakılmayan yerler. İki tane alert sistemi var. Birisi algoritmaya öğretiyor. False pozitifler üretiyor. Diğeri de radyoloğa buralara bakmadım, bir daha bakar mısın diyor.
Ki bunu hasta bazlı real time mi alert ediyorsunuz hekime? Hani hasta bazlı real time mi alert ediyorsunuz, yoksa hani görüntü bakıldıktan 2-3 saat sonra mı hekime bir geri bildirim gidiyor?
Bizimkisi tamamen yani research packs'te oluyor. Yani kliniğe girmesi için bayağı bir şey var. Hani süreç var. Clinical olması için işte FDA'den geçmesi lazım. Başka birçok şey var, prosedürü var.
Yani buna mesela hani hekimlerin,
bizim...
çünkü hani ben bir hekim olarak en büyük itirazım klinikte söyleyeyim, hani kötü bir anlamda demiyorum.
Hı-hı.
Şöyle bir şey oluyor çünkü hani mesela bir radyolog, biz şunu deriz hakikaten bir yasa olarak, önce görüntüye sonra klinik öyküye bakın. Ama mesela hiçbirimiz bir klinik öyküye bakmadan tanı koymadığımız için Hani
Evet.
her birimizin çünkü yaptığı ilk şey şu oluyor. Önce bir hızlıca görüntüyü geçiyorsunuz hani her yerine bakmadan. Bir
Evet.
genel kavrayışınız oluyor. Sonra klinik öyküye bakıyorsunuz, sonra geri
Evet.
dönüyorsunuz.
Evet.
Hani herkes önce şöyle bakıyor, kliniğe dönüyor, geri dönüyor. Hani bu tip
Evet.
bir biasla özellikle hani bu tip ikili bakışta veya ikinci, üçüncü dönüşü algılayabiliyor musunuz şu an?
Evet, ona geçeyim. Şimdi şöyle, yani nearly real time diyoruz biz buna, tam real time olmuyor çünkü radyolog bitirdikten sonra, yani görüntü screening'i bitirdikten sonra biz bu alertleri onlara gösteriyoruz. Sonra onların feedback'i varsa modele tekrar eklenebiliyor bu. Ama bu dediğimiz tamamen radiographical şey için, yani description için, radiographical interpretation için geçerli. Eğer başka dataları kullanmak istiyorsan onun için de şöyle, yani işte multimodal deep learning ile acaba biz bu sistemi geliştirebilir miyiz? Şu an zaten çok hot topic, yani electronic health record, genetics ve diğer bilgilerin, klinik bilginin radyoloji bilgisiyle birleştirilip diagnosis, prognosis yapılması şeyi biraz farklı. Yani onun için ayrı bir şey lazım, sistem lazım. Onu da çalışıyoruz. Bu mesela fibrosis için falan denedik. Prostat için de onu deniyoruz ama diğer şeylerde denemedik onu. Orada klinik bilgiyi koyuyoruz şeye. Prediction algoritmasına koyuyoruz. Ama bu eye tracking dediğimde hani sizin dediğiniz gibi henüz şey yapmıyoruz. Klinik bilgiyi koymuyoruz. Ama radyolog bakabilir mi tekrar? Bakar, feedback verir. O zaman modeli update ediyoruz. Evet.
Evet.
Öyle bir update'imiz var. İki türlü. Yani bir bakılan yer, bir de bakılmayan yer. Radyoloğun söylediği her şeyi record ediyoruz bu arada biz. Yani o mouse hareketlerinin hepsini, bunları bile record ediyoruz. Hepsini, bütün dinamikleri.
Ben de bununla ilgili bir soru sorabilir miyim? Bu radyologların baktığı yerleri anlamak için arka planda neleri kullanıyorsunuz? Çünkü yani bu gaze estimation'da da error rate'ler o kadar yani düşük değil. 3 derecelik açı bile aslında çok büyük
0.6
hatalara
baya
sebep
düşük.
oluyor.
Bu yeni şeylerle falan çok düşük. 0.6. Yani o 3 derece falan, onlar eskide muhtemelen. Bayağı düşük
Hangi
yani.
özellikleri kullanıyorsunuz acaba? Ne kullanıyorsunuz arka planda? Gaze estimation için arka planda hangi şeyi kullanıyorsunuz? Yani iris mi nedir?
Şimdi infrared gönderiyor 2 tane şeye. Şimdi önceki sistem şöyleydi. 3 tane triangle vardı. O aradaki işte irisin üzerindeki işte noktanın oynayışına göre şey yapıyorduk. Şimdiki sistem infrared işte gönderiyor. Gözün hareketlerine göre önce bir calibration şeyimiz oluyor. Onu söyleyeyim ben. Yani bu screen'in köşelerine koyuyoruz, böyle markerlar koyuyoruz. Siz onlara bir kere böyle bakıyorsunuz screen'den önce. Biz kalibrasyonu yapıyoruz. Yani sizin baktığınız noktanın pozisyonunu tam olarak biliyoruz, fiziksel lokasyonunu. Siz bakıyorsunuz 4 noktaya da. Sonra biz aradaki şeylere bakıyoruz, hatalara bakıyoruz. Ne kadar bir hata var? Sizin baktığınız yerle o koyduğumuz markerlar arasındaki şeye bakıyoruz. Bazen şöyle bir zorluk olur. Eğer çok böyle error varsa kalibrasyonda 1 derecenin üstünde falan, o zaman şu alnına koyuyoruz bir tane. Bir aparatımız var böyle çarpı gibi. Şöyle yapıştırıyoruz radyoloğun. Onu yapıyor. Onu da kalibrasyonu biraz improve ediyor. Yani çok hoşlanmıyor radyologlar o markerdan ama.
Bayağı kontrollü bir ortam o zaman sizin.
Evet, evet.
Teşekkür ediyoruz Ulaş hocamıza.
Ben
Bir sonraki
teşekkür
sunuma
ederim.
geçmek durumundayız. Tekrar çok teşekkürler hocam.
Ben teşekkür ederim.